Yeah.
Okay, I'll just start with our quick bureaucratic parts here. So it's conventional for me to just say a couple words about the rules, so to speak. The prepared part of the dissertation defense should be about 45 minutes. And we generally ask that during the presentation, questions of a clarifying nature are welcome, but not longer discussion points. Save the longer discussion points for the end. And I'll just turn it over now to Doug to introduce the speaker. Oh, sorry, one other thing. So I'm connected to the Zoom, and so I'll monitor the chat and be the learning coordinator or whatever that term was from LFA.
No, great, thanks. Yeah, so this is great. It gives me great pleasure to present to you Krishna Sanka, to have him give us a dissertation talk on Fluigi CAD and on all the microfluidics that we've done. So Krishna is an interesting student because as one of my older students, he represents the transition my lab made several years ago from focusing on design tools that would just take high-level descriptions and make biology, the tools that would take high-level descriptions, make biology and microfluidics. So we went from a lab that had no microfluidic capabilities, particularly in software, in both really software and hardware, but really needed to make that transition. So Krishna was vital in helping us make those core sets of tools that laid that foundation. You'll hear about that in this talk. So Krishna was not only excellent in helping us make that transition and doing that software engineering, but also Krishna was an excellent mentor, almost to his detriment, as he knows. Krishna at any given time was mentoring some 90 undergrads that I couldn't even keep track, but somehow he managed to juggle, keep them focused and be a good mentor. And he did that for 5, 6 years. He's done that for quite a long time. And I know he has a passion for working with young people and doing teaching. So getting a PhD was a good fit for him. Also, Krishna was someone who always filled in the glue. If we needed a server rebooted or something hosted or something done, as a group that has ECE students, BME students, MCBB students, not all of the students that I work with are familiar with computers, even though I'm an ECE professor. So Krishna was always someone I knew could get in there and take care of the plumbing and it would make it work. So like any grad student, it's always it's kind of not sad, but it's always a transition when we have students leave, but that's all part of the process. Krishna is going to be really missed, but we're looking forward to hearing his talk. And I know I'm going to keep him around a little bit longer to help us wrap up tools and publications and things. So thanks for all your hard work, Krishna, and I'm looking forward to your talk.
Thanks, Doug. I'm going to take off this mask because I honestly cannot breathe in it. Or at least while talking, I can't breathe. I guess I'm loud enough for everyone to hear, right? Okay. Hi, everybody. So as Doug already introduced me, my name is Krishna, and I'll be talking about this entire open source ecosystem of CAD tools that I've been building for way too long at this point. So, so just to give you some background about who I am and how I ended up doing all of this stuff. So back in like 2008, when dinosaurs roamed the earth, for most of the people over here, I started doing some electronics work as my undergrad, did a whole bunch of those things, had fun. Then in 2012, I worked from 2012 until my grad school, I worked at a string of startups doing all kinds of systems engineering and software development along the way. Then in 2014, I came to BU initially as doing more electronics, but then I kind of got sidetracked into photonics because it was more cool, it was more applied physicsy. And so I went about doing those things. And then somehow towards the end of my master's, I ended up in SciDart. It's like a whole story for another day. But, I spent so much time using design tools, like building electronics, writing software, doing all kinds of crazy engineering stuff. I was like, I have so many opinions about them. So maybe I could actually make better microfluidics design tools. And that's basically what my entire PhD has been. So I kind of channeled all my opinionatedness into like actually doing something more productive with it. So throughout this talk, you will see things ranging from microfluidics, computer engineering, and a little bit of biology here and there. But the main thing I want you to remember is that it's okay if you're lost. I'm spreading out the tutorials in different places so that it's easier to remember. because if I throw everything at you at once, it's hard to keep up. So starting over there. So let's start with what's microfluidics. I know most of the folks over here probably know what microfluidics are, but I'm sure like a lot of folks on the Zoom call don't really know what it is. So what are microfluidics? As a simple thing as the picture kind of entails, these are small plastic devices. And what you do with them is you insert small volumes of fluid into those plastic devices. And what the device will let you do is it'll let you manipulate and sense these fluids. And so whether you do any chemistry on it, whether you do any biology on it, or even if you do like nuclear physics on it, it's essentially just a way to move fluids around. And that is all you need to know for the time being. I'll be giving you more explanations of what it is as we go along. So where are they used? So they're heavily used in diagnostics, everything ranging from like a glucose sensor to a wearable, or even if you wanted to miniaturize like our entire COVID testing facility, could be done in a microfluidic device. There's a whole bunch of reasons why that's not happening. And what I'm doing right here is to make that more easy to do. And why is our lab interested? Like, as Doug said, we were doing a lot of synthetic biology. Well, why were we caring about doing microfluidics? Because microfluidics is a way of miniaturizing lab automation. So each one of these, the videos you see on the right are examples of droplet microfluidic devices. Now imagine each one of these droplets being a single biological sample you're doing an experiment on, okay? And each one of these videos are actually running 200 times slower than what they actually were recorded at. So that means that by the time you blink your eye, you can actually run about 1,000 different experiments. And if you actually translate that to how much time and effort it takes a biologist to actually do these mixing operations or actually doing all of this, it's insane. Like you could potentially automate like an average grad student's Ph.D. Entire lab work within like a couple of months if you had the entire microfluidic pipeline, but that is not the case. So the bigger reason about why you want to do biology is that my advisor is one of the pioneers in like thinking about engineering biology at like an electrical system. And so just like you have in an electrical system, you have different ways of engineering it, like different abstractions, like digital electronics, analog electronics. You think about it in terms of memory, communication, and whatnot. So let's say you wanted to engineer biology in all these different abstractions. You wanted to figure out a way to fit biology and engineering in the same way. You have a whole bunch of activities and you try to think about what metrics are actually important for that. And so when you actually think about what the activities are, they fall under like these specific these 4 work domains. One of them is specification, the second one is design, the third one is assembly, and the fourth one is verification. Don't worry if you can't keep up with all of this. We'll mostly never talk about this after this slide. But the main thing you need to take away is that in each of these things, the activity, having low volumes, being able to do long-term monitoring, and having precise environmental control is super important because you want your science to be reproducible. And so the metric you think about what is actually important as a researcher who's building these automation systems or building these research practices is that every practice needs to be repeatable so that if one person does it, the other person, like another lab, should be able to pick up the same protocol and do the same experiment all over again and repeat the science and make sure it's actually reproducible. And the second part is that it needs to have minimal training. You can't spend 6 months training a person to do a particular experiment when the experiment might only take like you a day to do it. So you need everything to be having minimal training. And that's where microfluidics kind of really shines, because as the name itself entails, microfluidics is talking about like small volumes. So you get that. You need minimal training because you're actually automating everything onto a device and you can program it to do what you want it to do. So it's automatable. Then because it's a device, a hardware thing, you can just take off the shelf, load it up and do your experiments. It's repeatable, and so on and so forth. But the most important thing over here is this little thing about researcher productivity. If you think about the average amount of time a life science engineer spends time pipetting small volumes of fluid from one pipette, from one well to another, it's horrible. Like I would never want to do anything that requires me to do pipetting. Even now, I kind of get scared when I have to do it. So the first question a lot of my friends over here and all of you would be thinking about is, how does one actually go about doing any kind of microfluidic design, right? Like I talked about these technologies, how does one make it? So The first part is always designing your device. And the way you go about doing it is, this is an example of somebody using Illustrator to make it. And yes, people use design tools like Illustrator to make these engineering devices. It sounds strange, but this is how it's actually done in a lot of places. And it's this person can, because tools like Illustrator are like pretty robust. Designers all over the world use them. They don't have bugs. They work very well, but it is really, really tiresome to do it. And this is like a very, very simple device, and it takes you so long to actually go about and make it. Because anything you need to do, you need to draw shapes, draw lines, and make sure you rotate them as it's over there and make it do what you want it to do. So now, as you can see, it is kind of tedious, right? Now, the smart people, folks with some mechanical engineering background, go about using tools like AutoCAD or Fusion 360 or name your favorite mechanical engineering CAD tool for actually doing these designs. Now, it's okay. Like these things, these tools speed up all the work you need to do. You actually can preview what the actual device would look like once you make it, and it's great, right? But what if you wanted to make devices like this? So these are kind of like the zoo of the most complicated microfluidics designs ever made. So, and they were only made like once, because the grad students who made them use tools like Illustrator, and they would never ever want to make any changes on these ever again, because just working on these designs is a nightmare. You want to change one parameter, good luck. It's going to take you forever to make it work. And so this is actually an Illustrator template of somebody from the Mo Khalil lab who used to make microfluidic devices with small well plates. And as you can see, the part on the left, the person used to actually draw everything and then manually make copies of selected features to make masks for using a nanofab in photolithography. Now, I don't think I would ever want to do this, repeat this process. So you might be thinking, you know what, Krishna, nobody's ever going to make those devices. For all I need to do, I just need to make like my simple device, and I can just use my Fusion 360 or my favorite CAD tool. Or you want to use Illustrator? That's totally fine. But when I think about why microfluidics CAD is actually important, so let's say you have an idea, right? You have a concept of what you want to do, like an experiment or some kind of a test you want to do. So you probably spend about, like a 3 clock symbols. I'm approximating it to like a week, just reading up different papers and literature about how these devices might work, who has done what in the field, and you come up with what we call an architecture of. So it's kind of like a high level idea about what your device should be. Then you spend about like a week making the layout, checking with people who can actually fabricate it, and seeing, if whatever design you actually drew is actually manufacturable. Then the second, then you spend, constant amount of time based on what fabrication process you're using. It might take a day, it might take a week to actually make the device. Then if you have things like valves and whatnot, and you have some automation associated with it, you need to spend some more time scripting the entire thing. And once you do all of this, you go into a verification step where you actually verify whether or not your device is actually useful. And then finally, once all of this is done, you actually put your biology and do it. And just to actually run your experiment, instead of using two well plates and like a pipette, this feels like a ridiculous amount of time to do anything. So now the issue is that it's not just this, right? In all these cases, there are different chances of having human errors being introduced. Like the saying goes, to err is human, and it really materializes over here. So in all of these steps, you could have a lot of errors happening along the way. And so whenever you have an error, or you figure out it's not doing what you wanted it to do originally, you end up having an iteration. And I guess it's probably the most computer sciencey part of my entire talk, where I say, so if you had to put an algorithm to cover from concept to execute, to characterize like from concept to execution, so that would basically take you a time of, like 5 clock symbols times the number of iterations, plus, the 4 constant clock symbols that will always take you. So, and that's where all the research I've been doing and what I'll be presenting to you kind of helps, because by having standards, you can get rid of these iterations, because for a fact that if you make the design in a certain way, it's going to be manufacturable, or, it's going to work in a certain manner. Then the second part is you have algorithms that almost nearly reduce all the human errors and greatly reduce the amount of time you need to spend actually making the design, and you can go about doing your own favorite hobbies or whatnot. So if we rethought that entire concept execution phase, as like a specified design and build process, as you can see in the slide over here, your time from concept to execution basically goes down to like the floor clock symbols. And that means that we can also do a lot of these things parallelly, auto-generate all of them, and get things done. So I'm not the first person to actually think about these things. My predecessor, Cassie, was one of the first people in our lab to start thinking about like a computational workflow for microfluidics. So in her work, when she started off Fluigi, what she said was, okay, from one of the design tools, synthetic design biology design tools called Cello, if we give it an input, can we make a microfluidic device that would do the test for that particular input design that you give it to it? And so what she did was she went all the way through from input, from giving it an input, from doing logic synthesis to actually generating like actual manufacturable masks. She went through the entire design process and made a device that could be used, that could in theory be used for testing those genetic circuits. But this was only in simulation. There weren't really any genetic circuits that we actually tested. So that's where I kind of came in, because I basically took Fluigi and instead of having it like a standalone tool, I converted it into a tool chain. What it basically meant was that I added two new description languages called LFR and Mint for describing microfluidics at different levels of abstraction. I introduced a standard called Parchment that would let different research groups and industry be able to share these designs and actually capture all the details that are usually missed in literature. Then I built two CAD tools called 3DUF and Neptune, which you will see some short demos of during the presentation, which allows anybody to go in and start doing it. We've had everyone ranging from like high schoolers to grad students use these design tools to make devices without hardly knowing anything about microfluidics. So if we think about this entire workflow, which my predecessor Kathy put together, we basically split up into like input and logic synthesis, physical design, and manufacturing and simulation. That's how she divided these things broadly. So in her work, when she did it for like the cello input, there was certain kind of input formats and canonization that was done for cello. So she knew exactly what the input would need to look like, and she knew exactly what the output needs to be generated for that given type of an input. So she created the entire logic synthesis step, and she basically hit it out of the park. She went all the way through, got physical design done, got everything done. So when I came in, I was like to kind of parrot like one of the things which my descendant, I guess, Ron said, what is left for me to do? So I was like, no, wait. If we needed to take the same tool and use it for CNC milling, it's not really synthesizing what we wanted to do in our droplet scenario. And maybe it's not going to generate for us like some other examples too. And it's not going to be able to, and we're not sure if the manufacturability is actually valid. Then we were like, okay, fine, let's try laser cutting, like what some of our friends at Mo's lab use. And we were like, okay, can we still generate the designs? Can we generate the layouts? Can we do that? And it was like so, like a lot of things were still up in the air. But when it came to like synthesis, you couldn't actually do it at all. And similarly, because the main platform which Cassie considered was photolithography, there was some promise for it to actually work in photolithography, but almost all of it was unknown. So the first part of what I did during my dissertation was basically I looked at how do we go and solve this manufacturability problem. If we made a design, we should be able to manufacture it. Otherwise, this tool is useless. Then the second thing which I did was I looked at, okay, can we improve the way in which the physical design is working? Can we extend it and make sure that we're getting design outputs for every kind of a device we throw at it? And the third thing that I did was I was like, okay, fine. Now we have this whole pipeline of algorithms and whatnot. Can we actually synthesize these things and have representations and formats which make sense? And so in order to do that, and that's essentially the like the contents of my entire dissertation. So at every now and then, we'll be revisiting that slide where we have the checkboxes, and we'll be looking at these things. So the first part, as I mentioned, was the manufacturing. So in terms of demonstrating the impact of the tool, I'll be having some two broad metrics, which I'm gonna hope to prove over through this talk, is that the tool 3DUF, which I designed, which I built for ensuring manufacturing, is usable and is useful. Then for physical design, the languages and standards I've developed actually make sure it's correct and is extensible. Then the logic synthesis section, for the logic synthesis section, the language and design tool I built, Neptune and LFR, are versatile and are kind of complete in terms of capturing what needs to get done for like microfluidic design automation. So we'll be first starting off with the manufacturing. So thinking about manufacturing, the first step, what we needed to do was, you saw how people typically drew, like design microfluidics. They were actually drawing on a canvas. So the first thing we needed to do was we needed to rethink how people were doing this. And what that meant was we essentially said that we're not going to draw anything anymore. We're going to decompose the designs into components and connections. That way we can store it as an object and utilize it. And what that meant is that when we each and every component would also be parametric, and it would allow us to do engineering on that was parametric, and it would allow us to do any kind of microfluidic engineering. So we created this entire library of components which we could use for any design. And the best thing was, because all these components were procedurally generated, it meant that it was scalable. That means that drawing the one on the right would have taken somebody forever to do. And so that's where you have the real power of using procedural design. So the next part was, okay, now we talked about rethinking the design, how we abstract it. What about the design for manufacturing? What we really wanted to do, right? So when we looked at the different manufacturing processes, we realized that all of them require different types of CAD artifacts, as in what is required for like the softwares and the downstream manufacturing process to actually manufacture it. And so what we did was we basically took every single component and connection and we started decomposing them into what we call features. And I assigned a DFM class to each one of these features to indicate what kind of a manufacturing capability it would have. And so now every component, because it's composed of different features with different DFM classes, you could individually track which component is manufacturable by what manufacturing process. And because they're all parametric in terms of geometries, you could also limit by just using like something as simple as a CSV file, whether or not it's actually manufacturable through a design process. So with something as simple as a for loop, we were able to generate all the CAD outputs necessary for any kind of design manufacturing process. And with the help, and it was so simple that even one of my undergrads, Liam over here, was able to extend it to include like integrations like electrodes, capacitors, optical elements, and whatnot. So it was something that could easily just expand very easily. So to summarize, we put all of this effort, like all these design thinking, all these software engineering, into an interactive design tool called 3DUF. And as you can see over here, this is me recreating a design which was seen in literature. I call it the Daradan cell trap, where basically somebody's trying to capture a single cell in the device design. And as you can see, within the span of 20 minutes, I was able to create this entire design. And this would have probably taken an engineer or somebody experienced in doing like CAD design at least an hour or so. And we could do, and every feature you see over here is parametric, which means that if you needed to change something, you wouldn't take that long to do it. And it's not just it's not just a drawing tool. Basically, we were able to show how you could actually do design of experiments with these tools, because we could integrate design like Taguchi design algorithms into it to generate variants. Then we could also basically evaluate like the flow and pressure conditions by the underlying device model beneath it by just adding some resistor models, which we put over there. And over the years, we've been able to replicate devices from literature. We had an undergrad team in a project called Mars, where they really knocked it out of the park, and they made over 200 devices, I think over 100 devices over the summer. It was crazy. There were like microfluidics everywhere. And now, more recently, we have a senior design project, a BME senior design project, working on an mRNA encapsulation device, which would be super portable and DIY friendly in the future. And it's not just that. We also were able to characterize what it actually takes to we created heuristics for measuring what the design effort is. And we were able to show how our design tool was actually able to reduce that design effort. Because anytime anybody talked about like, why do we need to make CAD tools? The biggest question in an academic circle was, what's the heuristic? What's the metric? And so we actually created these heuristic metrics for capturing how long and how hard it is to make these designs. And we published all of this under the paper 3DUF and in 2019. It was one of the top 100 downloaded articles in Nature Scientific Reports. And so, as you can see, through the work in 3DUF, we were able to address a lot of the issues that were missing in the manufacturing side. And I hope with the examples I've given, I could show how useful and usable it is. Next up, we're going into the physical design. So the first thing what I'd like to introduce is how do algorithms automatically design devices, right? So based on the premise that I gave earlier, like this, if this is a design, I said, okay, let's break it down in terms of like components and things connecting them as connections, right? So in case you were asking an algorithm to do it, the first thing that it would do is it would do a placement step where you would actually just describe all the components and all the connections between them as a graph. Then what it would do is, okay, then it would place them, and then through an algorithm, it would find the optimal positions for all of them, and then finally make the connections between all of those designs. And that's called routing. So what happened when we were trying to make updates to Cassie's place and route algorithms was that we realized that it wasn't working very well for all kinds of scenarios. And so when I looked into the literature and looked at, okay, what other papers were out there, and I was trying to evaluate them against, like what the design flow was, what the standardization was, what the algorithm was, and what the performance is. And I realized that there was something wrong with the entire standardization process. There was no standard way of doing anything. So this is a table that incorporates the 26 benchmarks all those papers use. And when you look at all of these things, you'll realize that different authors and different groups use different types of benchmarks. So even in the case, and almost all of them don't use the same benchmarks when they're trying to compare against each other. And even in the cases when people use the same benchmarks, it turns out the way they actually represent a component is very different. You might be like, okay, in an algorithmic world, does it even matter? It actually does. When you're doing physical design, these constraints on how you model the device, the component, makes a lot of difference. And the worst part is half of our component library won't even fit into these molds. So there was no way to actually utilize those designs, even if they gave me the algorithm, to just use it straight out of the box. So that started, so in order to start addressing some of the issues over there, we created a standard interchange format. Folks at UC Riverside and we created a standard interchange format. And then what we did was we created a bunch of benchmark sets. The benchmark is essentially a device description of what the components and connections are. And what we did was we basically ran them through both of our placement and routing algorithms. And when we ran them, unsurprisingly enough, our benchmarks worked very well with our place and route. Their benchmarks worked very well with their place and route. And that was like, okay, fine, this is great, but we need to figure out all these. And turns out like the reasons why they were failing were so many. It was everything ranging from like RAM running out of RAM, or like for some reason the layout was never actually getting like an optimal solution. It was all over the place. So we said, okay, we need a way to think about algorithm performance without actually getting into the weeds of the implementations. And so in order to do that, we came up with this analytical tool called benchmark spaces. So just to slow down a bit, a benchmark space is nothing but like a 3-dimensional space based on like some of the device properties. And every benchmark we have, every device design description we have falls somewhere in that 3-dimensional space. And what happens is that by just running all the benchmarks we have against a particular algorithm, we can draw a surface between the fails and successes and say that that is the algorithmic limit. So regardless of whether it's dying because of RAM or because it did not consider for a certain kind of connection density or whatever the reason might be, we know exactly where the benchmark, where the algorithm stands. So it's a very high level method for utilizing benchmarks and then just thinking of them in a different way. Now, this is something that could be used for like other algorithm development. And more recently, I was telling one of my good friends, Nick over here, that he could potentially apply something similar to this in his machine learning work, because you don't know exactly where things are failing. So if everything is unknown, just look at what your knowns are and just try to create like a space to characterize your algorithm performance. So in the true scientist and engineering fashion, the way we figured out how to formalize these benchmark spaces was we just tried a lot of different combinations. We tried putting together so many different three-dimensional views to see what are the best ways to separate stuff. And what we realized was that, and after a lot of trial and error, what we realized was that what we could do was we could take the device's graph characteristics and then separate them into two categories. One would be a graph structural property, which is essentially something like the number of components, connections, some kind of connectivity metric. And the second part would be some kind of a meta property that would be like a device spatial property. That would be like how big the component would be in the layout, or what the connectivity metric might be, or can we collapse a lot of connections into a bus, all those things put together. So what we then did was we said, okay, if you wanted to create a benchmark space, pick any two of these structural properties and pick one of these spatial properties. And now you have a benchmark space with which you could actually evaluate the devices. And so by doing this, what we were immediately able to do is we were able to evaluate every time we ran a new benchmark. When it failed, we were able to see what the patterns were. So as you see over here, in each one of these cases, like in simulated annealing, we realized that our design was failing when the component dimensions were too small. When they were too small, our optimization engine would just run overtime and try to over optimize it and never reach a good solution. Then in terms of planar embedding, what they realized was as soon as the number of connections increased, their planar algorithm was not able to find a good proper embedding. So it meant that after a certain connection density, their design algorithm would completely fail. So this is kind of how we started sussing out what are the more important metrics that we needed to do and what are the kinds of things we needed to go ahead and fix. And so the culmination of all of this basically made us put together this entire set of standards and the standard way of exchanging designs, benchmarking things, thinking about what the final benchmarks are, and also a generation tool, which my colleagues at the UC Riverside made. So, and it's not just that it's an interchange format for the design. We also try to future-proof it for like future applications in like specification, design, and like a design is what we were doing anyways, but in like specification and build to account for variations in manufacturing and how we might want to use it in different applications. So this second part, what we realized was kind of like this other issue, like algorithms were working so and so, but what really matters for any microfluidics engineer was the aesthetic of the final design. And that's actually one of the hardest problems to solve. And so what you see on the left is like a device description of a design, of the design on the right. So on the right-hand side is like a netlist description. It just represents what the components are, what the connections are. And on the left is like the actual device design it has. So let's say you take this exact netlist description and you give it to like a placement algorithm. It could generate layout something like this. All of them are correct as per what the netlist said, but they might not work, or they might not look nice, or it might make a really bad figure in a publication, so nobody might want to use it. So in scenarios like this, I was like, okay, let's look at how other people solve similar problems. So what I did was I started digging into like how analog VLSI folks thought about placements, because when you're doing analog designs, the exact symmetries and how you place the different blocks, every cell you place really matters. And if you don't do it right, it can really destroy your entire design. So everything is that sensitive. So I was like, okay, let me look at the most extreme cases of where all the aesthetics and all the layout details are important and see how they're doing it. And no surprise, what they had was what we call, they had a whole bunch of layout constraints to ensure that that the layouts would work out exactly over there. And so what we did then was we added to the Mint netlist description language, which we had, we added this entire constraint description language, and I formalized it, I baked it into the grammar so that it be formalized and always captured whenever somebody is describing the design or automatically generating the design. So that and that entire work effort has spun off these new this next generation of layout algorithms using like sequence pair representations and integer linear programming formulations to actually account for like these kinds of layout constraints and go that. This is ongoing work right now with some of our collaborators, and we are hoping by the end of spring, we'll have some really good results and will be part of our Neptune publication. So all of this work culminated into 2 papers, one being a conference proceeding and the other being an invited talk at ICCAD. So while for a field like physical design of anything, right, it's a constantly evolving space. Every year you have like 100 different, over a decade, you'll see about 100 different papers touting why this is better than the other. And so in that kind of field, I don't think I could have actually solved anything, but what I did definitely do was I set up some guides so that when people are doing their actual algorithm design, they have some idea about, okay, does this make sense for the microfluidics application, or are we just making algorithms that over optimize on metrics nobody cares about? So with that, I'll be now diving into logic synthesis, describing the tool LFR and Neptune. So the big problem with microfluidics, and this is kind of like a rant, I guess, is that, like the promise of microfluidics has been around for like almost 2 decades. Like everybody who's doing microfluidics, here's a promise of microfluidics at the beginning of the PhD, they get excited, they do a lot of microfluidics work, and by the time they graduate, they're like, oh shit, nobody in the industry wants to actually use these designs because, there's so many problems with it. So and when you actually go into industry, what you see are things like on the right, where you have liquid handling robots moving small volumes of fluid around. And so if with something like that on hand, the big question was, there's so many people doing all this microfluidic design automation work, what are the missing pieces? What's going on over here, right? Because of the ones which weren't the physical design, everything else was talking about synthesizing microfluidics. We're doing some architecture synthesis. We can solve all these cool new problems and do whatnot. And, that kind of captured in this little block of, what my predecessor Cassie kind of put forward, saying that, giving some inputs, and from there, doing some technology independent logic minimization and some technology mapping. So that's how she broadly placed it. And so after actually digging into this literature and, and a bit of wisdom and fails and whatnot, I realized that it's not just those 2 blocks, but it actually expands into something more, into more steps. And one of the bigger issues is that none of them use the same, and there's no actual standard input format or any kind of canonical form which everybody agrees on in all of this literature. So the big problems basically became, if you had the engineering know-how, if you wanted to do the engineering, there was an issue of how you wanted to communicate the problem. If you had an algorithm, there was a problem of, like how do people access it? And if you had an application, you had all these other things covered, right? Your algorithm or implementation would probably not work for the specific biological application somebody wants it. And so you have an issue of coverage. And so that's where it kind of came in, that's where the genesis of Neptune happened. So what we wanted to put together was this cloud-based IDE that would basically host all the algorithms and make it easy for anybody to access, have standard input formats so that people could just come in, use the same formats and run all their design tools, and also have coverage and make sure that you can actually fabricate the designs that come out of it. Now, the good thing is when we think about coverage, and based on a lot of the work that was being done in our group, what I could do was if we looked at all the component libraries we had, there was one interesting thing that we could take advantage of. It was that the distribution of these different components was very tight, which means that most of the components used by people are like this one small set. And in some designs, you might need something unique, but for the most part, there's the same components everybody's using. And so taking advantage of that statistical distribution, what I did was I created these 3 platform libraries. One is called DropX, intended for designing droplet-based microfluidics. The second one was MLSI for doing like tightly packed photolithography designs. The third one is a hybrid multi-layer platform integration, HMLP, which was able to like merge together millifluidic and MLSI type style device, photolithography style devices together. And so what I did was I basically created a bunch. I separated all these different components into their specific libraries. And what I did was I said, okay, now each one of those things is a primitive. Now, taking advantage of all the work that's already being done, which means that if you think of a primitive inside that platform library, you can get all the manufacturing info from 3DOF because it was doing all the DFM classes and whatnot, which I was talking about. Then if you wanted to think about the fluid dynamics, it would take advantage of my colleague Ali's work in using machine learning and inverse design for predicting how the fluid would, how the component would behave under certain conditions. Then we could also we could standardize all the microfluidic engineering knobs, right? Like what do you change, what can you change, what can you not change, using the standards we defined in our standard Mint library. And then finally, I also created these very rudimentary models, system engineering models of how you piece things back together and how do you create a device design from it. With this, we have only like these three basic models, which account for like what the inputs and outputs are, what kind of inputs and outputs are for every device design, which means that now we can basically abstract every aspect of every difficult aspect of engineering a microfluidic device in its own little tier, and people can keep extending each one of these tools and different libraries in their own sweet time. So the next part was communication. So now, so the big question was, can designing microfluidics be as simple as designing electronics? And for the folks smirking over here, like if you wanted to design electronics, you would probably write something like Verilog, and it'll synthesize the entire design, and you're happy. You just you go, you have it on an FPGA or whatnot, and you can do it. And so the big thing was, how do we do it for microfluidics like this? How do we make it as simple as doing this for microfluidics? And that's where my advisor was like, describe microfluidics based on how fluids interact. I can't do the imitation, but he said something like that. So out of that, LFR was born. So when LFR was born as a design language, I was like, okay, fine. How do I make this happen, right? Like I need to this is so abstract. So I started digging into literature, and what I did was I started borrowing vocabulary of what these interactions are and what they might mean from papers like Aquacore and whatnot. Then what I did was I borrowed some formalism from papers like BioScript, which is a programming safe chemistry language, and thought about how these interactions would work. What would it actually mean to like mix two things? What it means to like separate two things? And I borrowed some of the formalism from there. And then what I also did was I borrowed some of the relationship ideas, which Nada, one of who's on my committee, did in a master's thesis. This was actually one of I think it was a second or third paper I read during my PhD thesis, so during my PhD program. So it was kind of cool for me to be like, okay, you know what, that one paper I read back then, I could probably use something from there. And so what I realized was, while Nada had this entire way of describing instruction set architectures based on what the relationships between different fluid flows are, I was like, okay, fine, I don't need all of it, but I could use the and or relationships and just build on top of that. And so thus, thinking about Verilog, for those who don't know, is an interesting language, like any HDL. What you do in Verilog is you describe the device design. You don't literally tell it how to execute, but you tell how it's supposed to behave when some input comes into it. So one of the bad things about that is it's hard for people to start up with. But the good thing about it is that it's discombobulated. Like the entire syntax is all over the place. Like this syntax doesn't make any sense. And like from a programming design language perspective, at least for me, it's like, this is perfect. If I model based on that, I can describe a hardware device because I've done digital design. I understand how this is supposed to work, and I could think about what the abstractions would be. So now with LFR, which was modeled after Verilog, what I could do was I could define modular designs with standard inputs and output formats. Then I could scale these designs using vectors, because that was one of the big issues. Now, let's say you had 2 cell traps and you want to do something, and you want to change that to like 25 cell traps. How do you do that, right? Like you don't want to describe things all over again. So how do you describe those relationships? then the next thing was I wanted to be able to map things, because Verilog had all these little annotation syntaxes for ensuring clock timing and all that, gate timing and all of that. It's like, you know what, we can borrow a leaf from their book and, kind of, like optimize, what exactly we wanted to map to, give users some control over what needs to happen with it. Then, the other part was because Verilog also does some, math inside it, like some basic Boolean math and whatnot. I was like, what if it can do like basic fluidic math where, borrowing from the formalism, which I borrowed from all those different papers. And I was like, okay, fine. We could assign like our basic operators to like these specific interactions like mixing, sampling, or, like having some primitives like storage, which have some behavior models, which are like system engineering models, which I talked about earlier. So I was able to do all of that just through the syntax. Then finally, what I could do was just like how you had like these, the one cool thing about Verilog was that it had these blocks where you could describe the behavior, how the device would behave inside a specific block that would seem completely like a completely different syntax from the rest of the thing. And that was exactly what I wanted, because, in microfluidics, there's a lot of complexity going on. There's like what's happening in the flow layer, what's happening in the pneumatic systems that's controlling all of it, how all these interactions play together. And because of Nada's work in like formalizing all of those relationships, I could essentially synthesize a syntax that would actually capture all those relationships and be able to, or more like I could describe a syntax that would synthesize to her the relationships which she formulated in her work. So what now we have is, we have a way of going from, just like how you go from like Verilog to an electronics chip, we now have a way of describing microfluidics consistently well, taking all the vocabulary, considering relationships between flow, control, and all these different aspects of like a microfluidic device and everything. But now the big question was, now that I have a great language, how do we actually get from the language to the actual device design? All of that was great, but like that is the real problem, I guess, why I get the PhD, I hope. So the big thing for this was, so the way most people worked at, like mapping like a device, like a description to like an actual physical element was through something called technology mapping, which even my predecessor Cassie did in a certain way. But what we realized, so on the top is an example of Dagon, where you take a certain kind of logic circuit, and what Dagon would be able to do is would be able to map it to a different kind of logic circuit. So it's like a binary circuit input to a binary circuit output. One of my predecessors, Prashant, and friend Prashant, what he was able to do for one of his works in cello was he was able to use Daggerware rewriting to basically take any kind of a logic description, digital logic description, and be able to write it to map it to like a genetic circuit construct. And so the power of technology mapping was that, you could jump leaps and bounds with. But the issue was that microfluidics is not exactly digital logic. In both of these cases, your inputs were digital logic, your outputs were digital logic. The digital logic might be in different form, but it was still digital logic. But in my case, I had these issues of, everything was not the case, especially the interactions between like what the flow and control layers were. That wasn't digital logic anymore. While I could force feed all the other vocabulary and formalism into like a logic circuit type representation, I couldn't do that for the relationships. And so that's kind of where the entire synthesis workflow and this algorithm called ScriptSlate kind of came up, where we ended up having this two-step technology matching process where I would first map the primitives, the library primitives onto the logic description, and then from there construct the entire final device design from there. I'm not going to go into the detail of this because it'll probably take an hour for me to just go through all the steps over here, and not to even talk about the other hour or two it'll take me to go through the entire compiler steps. But what essentially happens is, let's say you wanted to have a device like this that you want to describe using this process, right? First, what you would do is you would basically just declare your module, and with that, and you declare what your inputs and outputs are for that. So through that, you kind of implicitly said what all your ports and everything are. Then what you would do is you declare all these intermediate locations, like flows and storages and whatnot, which these are like the connecting glue that stitch together all your functional blocks inside the device design. The next thing what you would do is, using the syntax the distribute syntax which I had, you'll be able to describe the relationships between different flows, and thereby generating these multiplexing inputs and outputs to the microfluidic device. Then what you similarly, because we wanted to have like a multiplexing to the storage, you would also be able to describe a smaller version of that using that. Then finally, what you would do is you'd use the assign statement and basically stitch together all these different functional blocks, which we described in the other places, and have your full device described through the process. So in order to do this, what we basically were capturing was what the logo you see up there is what we call the FIG, the fluid interaction graph, which is like this huge data structure that captures everything inside the LFR. Now, the reason we created this data structure was so that if somebody wanted to like put another automation tool on top, you don't want it to generate LFR syntax, because generating human readable syntax is harder, and it's easier to have a standard data structure which you generate to and then pipe it with more automation in the future. So what the fluid interaction graph basically captures is the structure. What the flow annotations from Nada's, like derived from Nada's work, basically captures a relationship between different flow and control layers. And finally, we have another item over there called the distribution tables, which actually captures the control logic, which drives each one of these control lines inside this microfluidic device design. So it'll be something like this. As I said, the top part captures the structures. Over here, we're showing all the relationships with some arrows going as more nodes over there. That's not exactly how it is, but I had this over here for easier representation. And the distribution tables were from this work by Minhas. And what we were able to do is basically capture all the control logic signaling that is required for it to happen in that format, all the connectivity graphs, basically. So now that we have all this information, how do we actually go through, right? Like that's the technology mapping. So we took the DAGON approach. And what I did was I basically modified what the inputs were, and I modified what the graph match algorithm was. And by just by modifying the inputs and the graph match algorithm, I was able to map all these things. And in order to do that, and finally, by having these different graph match candidates happen, what I created was this intermediate graph structure called a construction graph, which would map all the matches from the library onto like the actual fluid interaction graph. And then what I had were a bunch of coverage criteria, which I basically ran through every single primitive matching combination you would see over there to generate a series of netlists at the end, which would be the actual device descriptions, which can then be like pruned either via expert or by some criteria which we defined. In the case of what I did, I left it. One of the reasons why I wanted this to be an expert-driven system was that I realized that my PhD is going to be a finite process. There'll be some more, now that we're thinking about all these system design metrics and how do we engineer these things, there might be more intelligent ways to actually prune these results. For now, all I do is I have some, based on the coverage criteria and some other coverage criteria which I have, I basically prune the results for what I believe are optimally describing the entire device design, and you have a final result at the end. So the accumulation of all of this is planned to come out in this tool called Neptune, for which I have the video demo over here, is the cloud-based design tool where we're able to compile and synthesize different LFR device designs. And this is something we are planning to put out in the next semester. The preprint is already in the works. There was a bunch of feedback we needed to incorporate into it, but I hope you all will get to try and play around with the design tool once the preprint is out, and give us a lot of the feedback. My goal would be, somebody who has no clue about microfluidics, spend an hour reading the tutorials, be able to design microfluidics, and be like, okay, this is working. And so that's the kind of goal I want to get to eventually. So through this process, I was able to, through this entire process of creating LFR, Neptune, and orchestrating this entire design flow, I was able to solve a lot of issues in terms of like what the input canonical forms would look like, what the technology mapping process and all of that would look like over there. So I hope through the demonstration, so the talk I gave you, it kind of gives you some idea of, that it's actually able to, it's it's able to completely capture like what a microfluidic design is, and also captures like the fact that it's a versatile device language, right? Because now that it's an open language with multiple stages where people can do, where we can add more and more tools and design methodologies. And I hope that, in the next 5 years or so, we are actually able to just move away completely from manually describing device designs and going fully into like having these kinds of device designs. So if you took away nothing from this entire talk, right? What you should know is that now, because of the work I've done, if you have an idea, if you're somebody with an idea, what you're able to do is you're able to access one of my design tools online. You're able to seamlessly utilize all the design languages and whatnot, which are underlying in all these design tools. And then what you're able to do is you're able to generate designs which are actually fabricatable at the end of the day. And if you are somebody who's making like a microfluidic device, that's awesome, right? Like this is a device design you actually want. And then if you're somebody with a new microfluidic component, you can actually add it to our library. It's not that this component library is static, because everything is open source with a whole bunch of tutorials, especially one where I have an hour-long tutorial on how to actually add new components onto it. You can add it to the library. Or if you're somebody with a new algorithm, we have everything. Again, everything is open source. We have standard input formats. We are standardizing all the interfaces in all the stages. So you should be able to play around with if you have a new algorithm, you can hook it up with the rest of the tool chain, make it use LFR designs, generate the things, see whether it's working or not, and and basically utilize the same downstream pipeline at the end of the day for actually manufacturing your designs at the end. So that is what I've enabled, this mixing of all these different people who want to use things, like from the person with an idea to the user to the folks doing both microfluidic design research and microfluidic design automation research. So this is kind of like the bridge that covers all these spaces. As Doug said, I was building a lot of glue, and I believe this is kind of like the glue I've been putting together. So as I said, as you can see, there's still some things left out. And obviously, the part where, generating control pattern generation is non-trivial. And so what I told Ron, the new grad student, when he was complaining about Krishna, you solved everything, I'm like, listen, it looks like a single block over there, but if you actually dig into the literature, that'll probably turn into like another 10-stage process. So there's a lot of work to be done over there. And the other part where because my nature of being more hardware-y and more physicsy, trying to put a physics spin to everything, was that I was more interested in like how the behavioral simulations kind of work. And knowing the fact that I have only one PhD timeline to do this, I spent one of my courses exploring this idea. And what we did in that course was, what we said was, okay, everybody does behavioral modeling of microfluidics now using CFD. In our lab, we fabricate and see what happens, but for the most part of the world, we actually create COMSOL models and we simulate. So I said, so can we take Ph.D. and reframe the entire question into like a design verification problem and a design certification problem and a design fault detection and a failure detection problem? Can we do that? So that was the goal we had for that course. And so what we basically did was we modeled some of these designs created by my colleague Jing and modeled them as transition systems. And what we did was we just did a very simple analytical Monte Carlo simulation to see what different geometric parameters would define good and bad states. Because we had these transition models over there, wherever it's blue, it's a good state to have. Wherever it's yellow, it's a bad state to have. And what we saw was, as we just varied like the different dimensions of the height and width and different aspects of those channels and the junctions, we had this huge complex space where, we were like, oh, you know what? It's a very complex design space where we need to actually solve stuff. And so that made us start thinking, okay, now if that was a design space where we wanted to be able to identify an ideal operating point, right? How would we go about doing this? And could we do it with the machine learning models, which our lab has been pioneering? So what I did was I again dove back into my good old friend analog VLSI world. And I looked at what people are doing over there for formal verification. What I realized, what I pieced together as a story was that at the end of the course, unfortunately, was that if we represent the microfluidic circuits as these infinite space representations, then what we could do is we could essentially stitch together these model verification languages like STL and whatnot. We could put together a language that captures all that grammar, and we could use these hybridized ML models to actually verify whether or not the device would be a success or a fail, or like the failure detection and like the certification problems could be solved using these hybridized ML models. I really like to thank Martin for, so I need to like to give special credit to Martin for actually putting together all the Monte Carlo simulations and whatnot, and actually made me, didn't, like I didn't have to do all the simulation work, and it was really nice to work with him because he did a lot of the simulation work. That was his, he always does that. So we were able to actually evaluate whether or not this is a design problem we could actually solve. And we kind of got enough evidence to say that, this is a cool problem we could actually try different approaches for. And I'd also like to thank Professor Colin Bauta for actually giving us feedback on this entire process. So what could be coming out of that is that, like this part where I had, like constraining what the device operations would be for just telling DAFD, these are the performance constraints what I need to have for my microfluidic component, we could actually expand on the grammar over here and create a more complete microfluidic performance specification language that would just fit in place with the rest of the LFR syntax. And I think that would be a really cool problem, which I would do if I was doing another PhD, which I'm not. So the main thing, what I'd like to get out is, like why the work we're doing is super important. So when I think about all the work I've been putting in, why I strive to build this glue or put together all these systems and things so that we can do things better, is a story that comes to mind is one in Kerpai village in Orissa. So this is a village where I used to help fundraise for a health clinic in that area. So in that area, it's like it's like one of the most poverty-struck places in the world. And they have like a 90% incidence rate of malaria. And almost everybody is a tribal person, a person of indigenous origin or tribal origins, and they're all below the poverty line. So what the doctors over there realized was, the drug stopped working, and they didn't know if it was because like there was something else wrong, or is the drug resistance for the malaria parasite actually increasing. And the issue was that, like if that is the case, is it possible to actually check it? Now, what's the solution for this? They didn't have any way to do this. So like sitting here at BU, doing microfluidics, looking at folks across the river, building all kinds of cool therapeutics and technologies, the big question was, like there are technologies. In fact, what the paper you see on the left is done by somebody from BU, Vural, to actually detect like the antibiotic resistance, antibiotic resistance of bacteria. We could potentially modify it for like the Plasmodium parasite, which is there in which causes malaria. We could actually check to see, if the parasite is actually more resistant now. And by using the software tools and platforms which I have, we could actually put it together in like an entire one-shot, load everything, make the whole in vitro assay work on the device, and make that whole process automated in a small device form factor. But for some reason, this is not actually happening. Like these technologies exist, but nobody's actually integrating them for a solution. And the big reason is that apparently I'm missing a slide. So I will just talk about what it is. The big reason is that for academia, it's like so far away. Nobody even heard of that village until I talked about it today. For the most part, even the folks in this call. For startups doing this kind of work, it's too small. It's a poor people problem. It can't pay for their salaries. It can't pay for VC money. For people in the community to actually do this, it's super hard. It's not like, you just buy a computer and you just do Arduino programming and get your system to work. But when you're doing things like microfluidics and biotech, you need to know how to do everything. You need to know how to manufacture. You need to know how to think about the design. You need to know all these different things. So it's the same difficulty as somebody who knows digital design needing to actually create an entire small microprocessor. It need not be a very complicated one, but going from like circuit to gate is super hard. And that is the area, what I believe the tools we're building will actually bridge. And in order to do that, I partnered with some more folks in the community to create this, like this pseudo organization called Distributed Diagnostics, which is basically a community where we're sharing knowledge and we're trying to match people with mentors so that, we can actually utilize all the free CAD tools that I've been building so to help them doing manufacturing, share the knowledge and know-how we have within the community of how we do DIY manufacturing, and also make sure everything we're doing is actually reproducible. And that's where all the standards, which I've been harping about for the last 1 hour, really come into play. Because if one person does it, all the other people need to be able to do it again. Oh, there you go. This is a slide I was missing. So I said, it's like an alien planet for academia and whatnot. So I'd like to conclude with acknowledgements. Obviously, there are a lot. What I've done is not a one-person effort. I had so much help, which is not even to everything from like moral support, like talking about ideas, to like a lot of heavy lifting that was done by my undergrads. In fact, I'd like to especially acknowledge all the undergrads who I highlighted over there, because they not only did all the hard work, everybody did a great job, but they actually stuck around until the end to get a publication out or, get actual things working and not leave once, the semester is done. I'd also like to thank all the other folks, like the DAMP lab folks who actually, DAMP lab, Bill lab folks, Bill team folks, who helped me understand more of microfluidics and like synthetic biology along the way. I'd also like to thank all the collaborators I've been working over the last few years who are actually pushing all the aspects of, like the physical design techniques and everything, the standards work that we've been able to put together in all those cases. And I'd also like to thank, Professor Cullen Belta and Martin Sinclair for, letting me explore that little side jaunt of, can we capture the behaviors and what would that look like during the project, during the span of a course. I'd also like to thank my committee who has patiently listened to me talk about all these things, kept up with my crazy last minute kind of submissions, and will hopefully pass me after this. And I'd also, I don't know how to say it, right? Like for everybody, like if you're a 30-year-old man like me, but making like nearly nothing income, you need to have like a very patient family to be like, okay, fine, this kid is not completely gone. He's not a complete goner. He'll probably do something useful with his life. And like that's my brother on the right being very judgmental. I don't know. And those are my parents who have been very patient, who are always like, what, it's okay if things fail. It's fine. You don't ever have to worry about, the worst case scenarios. They've always been, the rock and the support and everything. I don't talk about it that often, but they are. My crazy extended family. And, Doug was asking how many of the folks on the call are, your family. And I was like, yeah, I guess a lot of them should have turned up today. I'm going to go after them if they didn't. So the thing is that, living in the US away from my parents and everything has been hard for a whole bunch of reasons. But, having a lot of family around was great. It's also bittersweet because, some of my family hasn't been here to see me through this entire process. There were losses and everything. And, it would have been great if they could actually see me get a PhD degree, probably the first one in the generation to get it. Yeah, I'm the only one in the generation to get it right now. I think there's one more niece of mine who will be getting, who's going to start a PhD program after me. So, like all of this wouldn't be possible, without all of these people in my life. And, like my advisor, Doug. I guess I'm the only person with this picture, so I had to use it. So, I'd like to put it out there. Like, Doug said nice things about me, but I've also been probably one of his most problematic students ever. Because, I'm just that insubordinate. I'm like doing whatever I want or whatever. Like, as you said, mentoring undergrads to my own detriment and whatnot. And, he's always been patient. He's given me the room to grow. I told him recently, like, it's funny enough because now I have the confidence to conquer the world. And that's what this PhD has given me. It's given me the skills which I know I can use in the future. And I'm already starting to see where all I can use it. And he's also given me the space, and he's given me more than anything else, the personal space to navigate a host of personal problems that I had to face during my PhD timeline. And I cannot be more grateful for having a better advisor than him. I couldn't ask for more. In fact, I keep saying, I probably wouldn't have a PhD if it's not for Doug. It's like a one-to-one match for sure. Like nobody else would have let me stay this long or do what I wanted to do. And, he also made the lab like a family. Like, we had a lot of fun, like a lot of strange things. And like family, we fought at times, but we always got each other's back. And, there's always positive things going on with the lab. And that has been something, like my entire social life in the beginning of my PhD. And that really helped support everything else that I did. And, I have to call out to the OG microfluidics gang. Like these were the people who started, like the microfluidics boys who started doing everything. I know they're all probably on the call right now, laughing and wondering where on earth did I dig this up. Funnily enough, the image is called regret. I don't know why. So, but this is there. Then I'd also like to thank Jing and Prashant especially, because during this last milestone, the last finish line kind of steps, if not for these two people, I don't think I would have finished my thesis or, or would have drowned in like a panic attack or whatever last night if I didn't actually have these two around to actually tell me, what, it's okay. You should get it's okay, fine, you'll do okay. And yeah, and that doesn't discount all my other friends for whom I don't apparently have pictures. Being somebody who doesn't take pictures, bites you back at weird times is what I've realized. There are all these friends of mine from like undergrad, school and whatnot who are there over here on this call. And, I just couldn't find pictures of everybody, which looked like, not like everybody were in diapers. Or, we're not really horrible. I'm like, good God, like you'll curse me if I actually put you up on a slide. So, I'd like to thank all of them. Like this wouldn't have been possible. Like this journey of a PhD and what my ambitions and what I want to have is not possible without all these people. And yeah, like if you don't see yourself over here, that's a signal for you saying that, you need to send me a good picture of yourself or with both of us in it, because, I don't take any pictures. And I think that's it for conclusion. I apparently also accidentally deleted my end slide. So if anybody have questions, please go ahead.
Yeah, we're happy to take questions from everyone, including the people online. We're in the knowledge generation and dissemination business, so I don't want to quickly shut down to just the community.
Yeah.
It's a fantastic talk. It's much better than yesterday's. I think that, one thing you talked about at the very end is how the power, this rapid development of microfluidics for diagnostic purposes and all that. And, using it in those settings comes with a whole slew of operational challenges. I think I've said multiple photos on Slack where like, I'll take a zoomed in photo of a microfluidic.
Yeah.
Nice, I zoomed out. I have 2 lasers, 6 pumps, a full like $10,000 camera. And so looking ahead on like building this for diagnostics, could you imagine any sort of like design for manufacturing often for each of the components? Are you looking at something for like design for operation, where different like components or different aspects of the design process? It's like, oh, you're going to need these X number of external.
Yeah, no, definitely. That's a very good question. So it kind of falls back into this part where I had, sorry, my computer's behaving pretty slow right now. So it kind of falls back into this way in which I described the primitives for engineering, right? So, okay, so it kind of falls back onto this. So this system engineering models not only capture how the microfluidic needs to be engineered, but also capture some kind of operational capability. Like if you look at the storage element, it assumes there's a carrier and a carrier over there. There's an input and whatnot. So when it comes to like actual number of like what kind of pumps you need for it, like what kind of valve actuations you need for it, I don't necessarily generate everything for like how it needs to happen for like pattern generation for like actual application. That's the job for Ron. But in terms of the actual hardware that needs to come out, you could standardize all the primitives saying that, okay, if you have this, I have only one kind of a port, right? But I could have like a specific variant of a port with specific dimensions or a 3D model attached to it. That would be a specific connector or an indicator, and you could do that. And in terms of like what pumping, like if you need to be able to pump it and whatnot, yes, like for the most part, we see all this crazy equipment going on over there. But one of the biggest issues in the field of microfluidics and industry is that the lack of integration, because everybody does this like a DIY sport, and people in the photonics world do it as DIY. People in the electronics world do something else. Everybody's doing their own thing. And so when you try to put all these things together, you have these huge boxes that you need to stitch together. But, you know, like our work with like Rabia right now is kind of paving the way towards integrating electronics first. But once you can integrate electronics, you can integrate photonics, because that's how you talk to any kind of photonic system. If you can do photonics, that means you can just use light to interrogate biology or whatever analyte you have. So it is doable. It's just a lot of work. And, you know, it might not give you the fancy Nature paper, but it might save 1 billion lives. So.
Oh, there we go. Yeah, do you want to invite Lakshman?
Yeah, a couple of folks. Oops.
So Lakshman can feel free to unmute and ask a question.
Yeah. Or was it accidental? So.
Or it may have been.
Really? So either people understood everything I said, or, you know.
Oh, sorry, there's a question typed.
Ah.
What do you think of best practices and platforms that need to be developed for experimental data storage and sharing?
Yeah, so that's actually one of the things we were trying to do in terms of yeah, so in terms of experimental data sharing. So this is kind of where the real issue with academia is, because by nature, academia is just everybody's trying to go against each other and trying to beat each other to the punch. So sharing data is not the usual way of operation for everybody. So I think the best way of doing this is just starting to open source data and start creating templates. Like the easiest way to do it is if somebody is designing, let's say, a droplet generator, create a template in which, you know, like your entire analysis pipeline would just work. So have an open source analytics package, like just the Python script you use for doing the analysis, have that on GitHub, link it to the Excel sheet, which you put up with the standard columns for inputs and outputs. And that's one of the things. And the bigger thing that needs to be taken in terms of like experimental data is that actually informing the folks, you know, like saying that, okay, you're missing out this one big parameter in that engineering paradigm. Having those discussions and engaging, I think that like just having conversations solves 1 million problems, in my opinion. So people can use, based on like what university you're in, what funding requirements you have, you might have different ways that you need to share it, but just having the standard schema is the first step for having all these data sharing things to work together very easily. We can definitely, I can go ranting about like what it needs to look like in an ideal world, but that would be the first step over there. Then I think there were another question for,
what were the criteria and metrics you had for determining LFR's ability to describe the design space of devices you wanted?
Yeah, so over here, It wasn't metrics as much as we were looking at different types of formalisms and the kind of graphs you could that you would need to make for describing microfluidics. So we realized that for like the flow layer, what you needed to be able to do was you need to be able to represent any kind of multi digraph with loops inside it. So as long as we could do that, that meant that we could represent any kind of a flow network. For control relationships, I kind of I had the cheat code over there because Nada's work kind of proved that they could do it for any kind of any kind of a microfluidic control relationship. So I just assumed that would be the case. And the third thing was interactions. So here, what I did was I actually put together a whole bunch of different protocol description languages, and I looked at how all of them were describing different interactions, what the instructions would look like, what the operations would look like. And I tried to synthesize something that was neutral to allowing me to describe actual hardware. I think I have a table somewhere in the back. There's a lot of backup slides, so I need to find it. Did I answer that sufficiently, Josh?
We'll take that as a yes.
Yes.
All right. So take another question in the room.
Could you go back to this slide where you were talking about like the fluid modeling and concepts like that?
Yeah, 1 second. I would also put take it with a grain of or a jar of salt warning because it's very early work.
Yeah. I guess my general question was, how do you envision models and algorithms that try to predict and capture the fluid dynamics to work with Neptune and overlay systems?
Yeah, definitely. So we already do this inside LFR right now, where we basically use DAFT as an inverse design tool. So as an inverse design library. So what an inverse design library is that all you need to tell to that software package is, this is the performance I need. These are the targets you need to meet. Give me the specifications I can use. That'll put it back in. So by querying DAFT, we get back these specific microfluidic design parameters, which we just put back onto the microfluidic component and change the geometries. By just modifying the geometry, we can basically meet those performance requirements. So in the long-term vision of what we would want to be able to do is essentially take a lot of these individual models, mesh them together, and that's where this whole hybrid ML model system kind of comes in, and have these kinds of transition models saying that, okay, we can basically partition this entire behavior performance into different spaces, and essentially say that, okay, for any given pressure or flow rate for a given component, it's going to have it'll be in one of those states. And by actually just monitoring what state transitions happen at what boundaries, we should be able to stitch together a larger model. So basically mesh together multiple machine learning models and actually create a complete model for identifying whether or not your device will have failure, whether or not your device would be certifiable. So the pie in the sky goal for certification is that if you had that working, let's say for a set of say 10 components, which are used for in vitro assays, it means that you can automate the FDA process. So if you can automate the FDA process, that's $1 billion company right there.
So the idea isn't to, you pump all this information to DAFT gives you the geometry that you need, as opposed to you making the device and then simulating the
Exactly.
Right.
So a lot of it is going to be based on what prior model and information is there. And, instead of actually doing experimental data, you could fill up DAFT with just COMSOL simulations if you want. But it's only going to be as good as the model inside COMSOL. If you do experimental, you got nature's model. So you actually capture whatever that is.
All right, we can maybe have up to a couple of more minutes with the full audience. Sure. If there are no other questions, we can thank the speaker again and thank the audience. and excuse the audience. Or microphone, so on. So people online,
I mean, except for Nada, everybody else. gotta
everyone
go.
else should drop off.
I'm gonna stop. Thank you.
We're back to the tripod. Thank you for joining.
Gonna stop the recording now.